In this video, we'll look at the keto-enol tautomerization. So, this would be my keto form. And this would be my enol form. And these guys are in equilibrium through the movement or migration of one group. And in this case, the group is an H atom. So it doesn't necessarily have to be the exact same H. But we see that the H goes from this alpha position right here to on the alcohol right here. So keto, enol, and these guys are in equilibrium. Generally speaking, the equilibrium favors the keto side, which is why I have the arrow pointing to the left as larger. There are a couple cases where it doesn't favor the keto side. So we're going to look at how does this migration happen, and we're going to do it specifically under basic conditions. So under basic conditions, we're actually going to form something called an enolate ion. So if we look at this starting place here, this proton's at the alpha position is actually somewhat acidic because of the resonance structures that are formed upon deprotonation. So what we can do is we can put in solution a base. So let's just use hydroxide. And this hydroxide ion can come in and deprotonate that alpha position. And so when that happens, what I get next door is this compound, and this is in resonance with this compound. And this guy on the bottom here is called an enolate ion. So under basic conditions, the hydrogen won't protonate that O minus. It's just going to remain as a negatively charged oxygen. And so this alpha hydrogen is deprotonated, and I get these two resonance forms. The bottom resonance form is going to be stable, that enolate ion, because the negative charge is more stable on the more electronegative oxygen than on the carbon atom. So I can get this enolate ion intermediate, and then we'll see in class how this can go on to react with other species. But one thing that I can do is I can label based on this acidity of this proton. So what I can do is I can substitute deuteriums for hydrogens. So as an example, let's say I have cyclohexanone, and I'm going to put this in solution with some sodium hydroxide base under basic conditions, and then I could put it in with CH3OD. So I'm going to try to label this, and I'm going to put this methanol in excess. So methanol has a slightly acidic proton, in this case deuterium, that can be pulled off. What we'll see over time, if we let this stir for an extended period of time and we have excess, is that all of these protons that were at the alpha position will end up getting replaced by deuteriums. And so because this is a different isotope of hydrogen, we call this a labeled compound now. So we are swapping a proton for a deuterium. So this would be a different isotope of H. So using the acidity of the protons that are at the alpha position, right here, I am able, oh that's a horrible alpha, yikes, to deprotonate and then replace them with a deuterium. So we'll look at that enolate ion again and see exactly how this happens. So under these basic conditions, I'm just going to draw one of the H's that I want to use here. I've got sodium hydroxide in solution, so that sodium hydroxide can deprotonate. What you'll sometimes see is that it deprotonates and these electrons fold down and these fold up. This is the favored resonance structure, the enolate ion, that I'm going to draw because it is more stable. And so that's one way that we can draw that intermediate. So again, here is our enolate ion. And then what happens is we're in solution with some methanol, so we have CH3OD. this deuterium is a little bit acidic, and so what happens is the lone pair of electrons on the oxygen folds back down, and this pi bond can come grab that deuterium and deprotonate the methoxide. And so what I then get is this guy plus methoxide, which can just go act like a base because we're already under basic conditions. So then you would see that this would happen 3 more times, and that would get me my final completely deuterated compound. So I can label by virtue of that acidic proton that is next door to the carbonyl compound. As we said before, the keto form is favored. The carbon-oxygen double bond is more stable than the carbon-carbon double bond. And so that is what makes the carbon get deuterated instead of the oxygen. So we don't see this oxygen up here getting protonated under these circumstances. We see the carbon getting protonated, or in this case, deuterated. So this can also happen under acidic conditions, and I actually did an experiment like this in graduate school. So we can do D plus and D2O. So under acidic conditions, the first thing that's going to happen is this oxygen is going to get protonated, or in this case deuterated. And so I end up with this compound. And what happens then is I have resonance structures here. And I get a positive charge there. Once that full positive charge has been made, then I end up using my water, which is the strongest base I have under these acidic conditions, to deprotonate. And it makes my Enol. So it's actually going to be deuterated or protonated, in this case deuterated, because it's under acidic conditions. So we won't have any negative charges under acidic conditions, only under basic conditions. Now this enol can react the same way. We can remove the deuterium and deuterate it as well.